And we're now recording. Okay, so we are down to one last exam. You should have gotten your exam scores last weekend. If you didn't, let me know. And you should have gotten the solutions if you wanted to look at them also. I sent that over the weekend. Okay. So game plan, we are now up to here. I already did some of 16.4. I think I can do 16.4 and 16.5 today. Okay. For now, the game plan is to have the last regular exam on Thursday the 13th. Let's aim for that. Then the 18th, we'll just do a review for the final exam, some questions and answers. Final exam on the 20th, and we are done. Okay. We're getting near the end, and I already did some of 16.4. I'll go back and do that now, and then go on to 16.5, hopefully. Okay. And so, judging from the remaining calendar, so it looks like we'll have 2 more quizzes. Quiz Thursday on 16.4 and 16.5, and quiz on May the 6th, and that will be our last quiz because the remaining Thursdays are exams, Thursday the 13th and Thursday the 20th. Okay. Now, for some reason, something goes wrong and I can't finish everything by the 11th. So it's not my preferred way to do it. I could still push the test back to the 18th and then have the final exam on the 20th still. So I've got one buffer day sort of to get everything covered there. Okay. All right, so 4 exams down, 1 more and the final exam. Okay, so any questions about that, please? Check. Okay, some people just joined. Yeah, just go ahead. What happens if we finish early? Okay, I don't know if we're very much ahead, but somewhat ahead. Okay, so but if everything goes according to plan, we may end any individual date somewhat early. So yeah, that might happen. Now I can't give the final exam early. That's not going to happen. Okay, but yeah, I'm still a little bit early, but we'll see how it goes from there. Quick word. I did say you get to drop an exam, and so there are some of you who have gotten A's on the first 4 exams. In case you're taking that attitude, I can drop 1 exam, so I'll just skip the 5th exam before taking the final exam. I set up the point system, if you look at it more carefully, that the final exam is treated as so many tests. Now, I forgot how many it was, but whatever I put in the syllabus, let me see if I can find it here. Okay, so I know some of you might be thinking of the game. In any event, it is to your advantage mathematically to do well on exam 5 and the final exam. Okay, so let's see. Final exams were 300 points. So there's 700 points available for exams, so to speak. Okay, so the way you want to think of it is you have 500 points for the exam, and the final exam, you're taking 1 exam, it's worth 300 points in the form of 3 100-point exams. You're not really taking 3 tests. You're taking 1 test, that you will get 1 score between 0 and 100, and it's like taking tests 6, 7, and 8. So let's pretend on the final exam, you get 80. Okay. My grade book will show 80, 80, 80. Okay. If you get 100 in the final exam, it'll show 100, 100, 100. That's how it's worth 300. If you skip the final exam, it goes 0, 0, 0. Okay. So that means you have 8 scores, and then out of those 8, you get to drop the 1 lowest. So that's the way it works. Okay. So even if you got A's on the first 5 exams, you say, I'm going to skip the final exam. That counts as 0, 0, 0. You get to drop 1 of the zeros, but not the other 2. And of course, you know, and I know that zeros aren't very good for your average. Okay. And you can show mathematically that if you decide to skip out on test 5, you can do that. That puts more pressure on you for the final exam. If you do test 5, for those of you that have been doing well, and you do well on exam 5, then you don't have to score as high on the final exam as you would have if you decide to skip the exam. Okay. For whatever it's worth, you can just take my word for it. It's to everyone's, and I intentionally made it that way because I know some of you might have the attitude, oh, I'm getting A's on every test. I'll just skip test number 5. I've constructed my point system so that it is mathematically to advantage to do well on every test. Okay, so just a little side note for that there. Okay, And let's see, anybody else join? Okay, so yeah, any other questions about what's happening and whatnot? Okay, so going back to 16.4, so you have your 4 exams. We have exam 5 and a final exam, which is worth 300 points, but think of it as 3 100-point exams, so to speak. Right. So back to 16.4. The main theorem is Green's theorem in the plane, page 1096. Let me close the chat because it's in my way. So integral along a curve, positive orientation, which means counterclockwise, p dx plus q dy. That's sometimes written as f dot dr, which is work for you physics people. Okay. The f is sometimes used as force applied to a distance, dot product. Partial of q with respect to x minus partial of p with respect to y dA. Usually it's easier to do this part. Okay. So I did some problems last time and we do the rest. Okay, so let's see. Yeah, the last one that I did fully, I think, was question 9. So let me just go back and review that. So integral along a curve of y cubed dx minus x cubed dy. I want to emphasize that in 16.4, it's only in a plane. This is Green's theorem in a plane. There's an equivalent version in 3 dimensions. That'll be section 8. Okay, it's something called Stokes theorem. We'll worry about it when we get to that. Okay, so this is p dx minus q dy. Okay. So rather than integrating around the curve, it's a lot easier to use the theorem and say partial of q with respect to x minus a partial of p with respect to y. That's negative 3x squared minus 3y squared dA. Factor out the negative 3. And then you have x squared plus y squared, which in polar coordinates is r squared. R dr d theta. This is a circle center of the origin of radius 2, so r equals 0 to 2. Theta is 0 to 2 pi. These are all constants. There's no theta involved, so take out the length of the interval of theta, which is 2 pi minus 0, 2 pi, so negative 3 times 2 pi. Integral of r cubed dr. That's negative 6 pi r to the 4th over 4 from 0 to 2. Plug in 2, you get 16 over 4, which is 4. Plug in 0, you get 0, negative 24 pi. Okay. As I mentioned, I started problem 11. Okay, it was a nice problem, but it got to be pretty long real fast. Okay, so I said skip it. Okay, so the only other ones I was going to do was 13 and 17. Then I'm done with the section pretty much. So 13, f of xy is y minus cosine y x sine y. That's p and q, by the way. So y minus cosine y, that's p. X sine y is q. I can't point it out to you because I'm holding up the book. C is a circle, blah, 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 oriented clockwise. Notice it says clockwise. That's considered a negative orientation. Okay, so I have to keep that in mind. It doesn't really affect the problem that much. It's actually a pretty easy problem. Okay, so this is P and this is Q. Yeah, I can write that down. This is P, this is Q. Okay, so partial of Q with respect to X, sine of Y, minus the partial of P with respect to Y. Partial with respect to Y is 1 plus sine Y. And when I subtract, I get negative 1. That's nice. So the integral is negative. Now that negative comes because it said clockwise orientation. Right? I can't find the problem that I was looking at. 13. Orient it clockwise. That's a negative orientation. However, this partial of Q with respect to X minus the partial of P with respect to Y came out to be negative 1. So the negative of negative 1 dA, I'm just integrating dA. Integral dA is A. Okay, so I just want the area. And if you look at this equation, That's a circle centered at 3, -4, whatever. The meaning is the radius is 2. I'm sorry, I should have had a second integral symbol because it's a double integral. Double integral. Okay, so what's the area of the circle? Radius is 2. Okay, so it's 4 pi. That's it. Now this is actually the wrong formula. I should say pi times 2 squared, which is 4 pi. So the answer is 4 pi. All right, then 17 was the last one. Then I'm done with the section pretty much. So 17, use Green's theorem to find the work done by the force F of xy is blah, 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 in moving a particle from the origin along the x-axis to 1, 0, then the line segment to 0, 1, and then back to the origin. Okay. The picture's like this. So here's the function. I thought it was easier to multiply that out. So x squared plus xy, xy squared. Okay, I lost the I and the j. That's p, that's q. From 0, 0 to 1, 0 to 0, 1, and then back to 0, 0. So this is counterclockwise. Therefore, that's positive orientation. All right. So using the theorem, let's see. This is y equals 1 minus x. That's pretty easy to see. Slope is -1. Y-intercept is 1. So I want the partial of q with respect to x minus the partial of p with respect to y. So partial of q with respect to x is y squared. Partial of p with respect to y, that's nothing. That's x. So y squared minus x. So I'm integrating y squared minus x. Right. So I have the double integral. Y goes from 0 to 1 minus x. Our favorite is to do y first. And then x goes from 0 to 1 of y squared minus x dy dx. Okay, so that's pretty straightforward. Integrate with respect to y cubed over 3 minus xy. I'm going from 0 to 1 minus x. Plug in 0, you get 0, so forget about it. Plug in 1 minus x. 1/3 1 minus x cubed minus x times y, which is 1 minus x. So this is a little bit clumsy, but it can be done. Okay, first let me distribute that as negative x plus x squared. Okay, so I'm going to leave that alone. Negative x plus x squared. Okay, I could multiply that all out. I don't feel like it. Let's just integrate as a power root and the chain root. So the integral of 1/3 1 minus x cubed is 1/3 1 minus x to the 4th over 4, and then by the chain root times -1, right? Which is the derivative and the antiderivative of the inside. And this is minus x squared over 2 plus x cubed over 3. Okay, this one you have to be a little bit careful. When you plug in 0, you don't quite get 0. When you plug in 0, that's 0, that's 0, that's not. Right, that's 1 times 1 over 12, so it's a negative 1/12. When I plug in 1, this is 0. That's nice. So I have negative 1/2 plus 1/3. So final answer is negative 1/2 plus 1/3 minus a minus 1/12. That's negative 1/2 plus 1/3 plus 1/12. Common denominator is 12. Negative 6 plus 4 plus 1. Final answer is negative 1/12. Okay. So that's the answer. And I guess a side note, this would not be considered a conservative vector field, right? If I go along any closed path for a conservative vector field, you should get a 0. This one was negative 1/12, so it's not. Okay. And of course, the other thing we already know from the formula is we're doing the partial of q with respect to x minus the partial of p with respect to y. Right. Well, that was a criteria for conservative vector fields. Right. If partial q with respect to x equals a partial p with respect to y, then when you subtract, you get 0, which means there's really nothing to do. Okay? Which means most of the problems in this section are non-conservative vector fields, obviously. Okay. All right, so I'm done with 16.4. Okay, so I can mark this off. Getting near the end. 16.5. Now, some problems are still to do really, really long. Okay, so we're almost there, but we have a few quote unquote really long problems to do. I mean, you got to do some long word problems and so forth just to kind of feel what it's like, I guess. Okay, so what's 16.5? All right, so the main topics are something called the curl and divergence. Page 1103. Curl. We're in 3 dimensions now. If F, notice it's a bold F, which means a vector, is PQR, PI plus QJ plus RK. Now, this is a definition of the curl, but I do not want you to use it. Repeat, don't use it. I want you to use the determinant form. And when you do it for me on the homework, quiz, or test, I need to see the determinant form. So even though this is correct, I don't want you to use it. So don't even look at it, so to speak. You may have this, number 2, curl F is del cross F. It's a strange cross product between something called del and F. Del is a vector, partial with respect to X, partial with respect to Y, partial with respect to Z. And here it is. Okay. So see that 3 by 3 determinant? That's what I want you to use for curl of F. Frankly, if you had to memorize it, which I'm not making you do, but if I had to make you memorize it, who's going to memorize that, right? But if you all know how to do a 3 by 3 determinant. If you do the 3 by 3 determinant, you are essentially doing that. Okay, so ground rules, the Melvin-Hom ground rules. Okay, whenever you do a curl, I need to see the 3 by 3 determinant. Okay. Yes, if you take some other teacher, they may not require you to do that. I'm requiring you to do that. So I must see the determinant once you go to see that you know how to do it by the determinant method, not by doing this. Okay. So the top row is always the same, I, J, K. The second row is always the same, partial with respect to X and Y and Z. And the bottom is P, Q, and R, the components of F. Okay, so if you can kind of see how this strange cross product works, it's I times that minus that, partial of R with respect to Y minus partial of Q with respect to Z. I know it's not quite focused. Okay. Minus, I know it says plus, but we reversed it already. Minus partial of R with respect to X minus the partial of P with respect to Z. Okay, so negative all of that. And then K times that minus that, partial of Q with respect to X minus the partial of P with respect to Y. Okay. So that's something called the curl of F. Let me give you an example here. Capital F of x, y, z is a vector function, xzi plus xyzj minus y squared k. Find the curl of F. So curl of F, you can write del cross F. Top is always ijk. This is always partial with respect to x, y, and z. And these are the components, p, q, r. So it's the partial of negative y squared with respect to y minus the partial of x, y, z with respect to z, I, minus partial of negative y squared with respect to x, minus a partial of xz with respect to z, plus partial of xyz with respect to x, minus a partial of xz with respect to z, k. That's the way it works. So partial with respect to y is negative 2y, minus partial with respect to z is xy, I, minus, okay, partial with respect to x, there is no x, so that's 0. Partial with respect to z is negative x, so it's negative x, so it's going to become a positive x. And then partial of x, y, z with respect to x is y, z, minus partial of x, z with respect to y. There is no y, so that's 0. Okay. And so you have it. So negative 2y minus xyi plus xj plus yzk. Okay. All right, so what's so good about having this curl? There's one good thing, and you can put this on your next cheat sheet. If f is a function, little f is a function of 3 variables that has continuous second order partial derivatives, then curl del f is equal to, notice it's the 0 vector, it's bold. Okay. So the object that comes out of doing a curl is a vector. It's the 0 vector, 0, 0, 0. Okay, and it's pretty easy to prove. They went ahead and did it. Doing it with a 0 vector. So that leads to this theorem. So in 3D, okay, I mentioned this a while back. You know, if you have a 3-dimensional vector, how do you know if you have a conservative vector field? Now we know. If capital F is bold F is conservative, then the curl of F is the 0 vector. This gives us a way of verifying that a vector field is not conservative. Okay, so if you're given a vector field, capital F, in 2D, we know what to do, right? Partial q with respect to x equals partial q with respect to y. How about 3D? The curl of f is equal to 0. That means there's an anti-curl. And we went through the proof here. If you have little f and you have well-behaved functions, the curl of del f is equal to the 0 vector. Okay. Right, so this is how you would prove that you have a conservative vector field in 3D now. Find its curl. Obviously, there's a lot of work there, as you can see. And curl f is the 0 vector. Okay. The converse is theorem 4, it just goes the other way. Okay. If bold f, capital F, is a vector field defined on R3, you have continuous partial derivatives. If curl f is the 0 vector, then f is a conservative vector field. That's what you do. So you do this thing, this 3x3 determinant. Okay, and I'll just mention off to the side one thing. When you're doing this in, so let me look at definition number 1. Okay. If you're in 2 dimensions, then the k component is 0. In other words, the R is 0, right? It doesn't exist. Is that right? If you're in 2 dimensions, there is no R. Let's take a look. So that means that's 0. That's 0, no matter what. That's 0. Partial of z, there is no z. That's 0. Partial of R is 0. So the only thing of substance is the last one. Okay. And that's exactly what you have in 2 dimensions, right? So this is all gone. That's gone, that's gone. Okay. So the 2-dimensional flavor is partial q with respect to x minus the partial q with respect to y is equal to 0, which means they're equal to each other. Okay. Because in 3D, if R is 0, that's 0, that's 0, that's 0, that's 0, right? That's 0. There is no derivative with respect to z. So that's just a 2-dimensional flavor that we already saw. Okay. Okay, and then something called divergence. Page 1106. So if you have a 3-dimensional vector, f, pi plus qj plus rk, the divergence has this definition. Put this on your next cheat sheet. Div f is the partial of p with respect to x, plus the partial of q with respect to y, plus the partial of r with respect to z. The thing that comes out is a scalar, not a vector. Okay, and sometimes you can write it as del dot f. Okay, so the divergence is a dot product, del dot F. The curl is the same thing. I don't think that's running back the page, but it's del cross F, the vector. Okay, and one more nice theorem. You can put this in your cheat sheet, although there's not that many homework problems at the bottom yet. If capital F of Pi plus Qj plus Rk is a vector field in R3, P, Q, and R have continuous second order partial derivatives, then the divergence of curl F is equal to 0. Notice it's the number 0, not the 0 vector. Okay, so divergence of something comes out to be a scalar. The curl gives you a vector. So div curl F is 0. They proved it regardless of any function that you have. They showed it, and you always get 0 in these cases. Okay. All right, so I think I'm going to get started with these problems. So 16.5, let me take a look at our homework sheet. What do we have? Just 1 to 7 odd, 13 to 21 odd. Okay, and by the way, your quiz on Thursday will be on this kind of stuff. Mostly. Okay, so we only have to go up to problem 21, it looks right. Page 1109, for those of you who don't have the book and aren't getting it. That, oh, I don't think you had to do any of those. Let me check. 1 to 7, got that. And 13 to 21. You determine if you have a conservative vector field. All right, so that's that up and down stuff we talked about. 4. And there's 19 and 21. Okay. And I'm going to put the book down because it's heavy. All right, number 1. So capital F of x, y, z is x, y squared, z squared I plus x squared, y, z squared, j plus x squared, y squared, z, k. This is P, this is Q, this is R. Remember, if you have the vector R, R is a position vector. So the components are automatically x, y, and z. Of course, you can tell right away, this can't be x, y, and z because they got x, y, and z all mixed together. All right, so it says find a curl and divergence in directions. Find a curl and divergence. Okay. So curl del cross F. And this is exactly the way I want you to do it. Okay, show me the determinant, not just by the definition that I showed you earlier. So the top row is always ijk. Next one's also partial with respect to x, y, and z. And then p, q, and r. So x, y squared, z squared, x squared, y, z squared, x squared, y squared, z. Okay, so I component is that minus that. So partial with respect to y is 2x squared yz minus that, quote unquote, times that. It's not really times, but you just apply the derivative. So partial with respect to z, 2x squared yz minus parentheses. So that times that, it's really a partial of x squared y squared z with respect to x. That's 2x y squared z minus that times that, quote unquote. Again, it's not really a multiplication, it's a derivative. So derivative with respect to z, 2x y squared z. And then k, that minus that. So partial with respect to x, 2xyz squared minus that derivative with respect to y is 2xyz squared. Okay, and they're all 0, so you get the 0 vector. Which incidentally now means that, yes, this is a conservative vector field, which means we can find an anti-gradient. And we'll be doing some examples of that a little bit later. Anti-gradient does exist. Okay, then the divergence. Divergence of F is usually a little bit easier. Del dot F. So del is this. F is PQR. So you just put a P there, a Q here, an R there, and add them all up. Partial P with respect to X plus partial Q with respect to Y plus a partial R with respect to Z. That's all. So partial with respect to X, Y squared, Z squared. Partial of the middle one with respect to Y, X squared, Z squared. And the partial of R with respect to Z, let's see. Somehow I don't think I did that right. There's not supposed to be a square there. Sorry. It's X squared Y Z. So X squared Y squared. The square is supposed to be on the Y. My bad. That should be the square. To there. Yeah, I wrote it wrong. So there wasn't anything wrong with my math. There was something wrong with the way I wrote it. Okay, so Y squared Z squared plus X squared Z squared plus X squared Y squared. It doesn't look like anything combines, so that's it. Okay. See if I can find, digress just a little bit here. Here. Yeah, I'm not really testing you on this. Your physics teacher might. The reason for the name curl is that the curl vector is associated with rotations. One connection is explained in exercise 37. Another occurs when F represents the velocity field in a fluid flow. Particles near X, Y, Z in a fluid tend to rotate about the axis that points in the direction of curl. Okay, and the length of this curl vector is a measure of how quickly the particles move around the axis. So, very crudely, take a look here at figure 1. The curl measures the tendency of a fluid to rotate around an object. The bigger the curl, the more the tendency. So if the curl comes out to be 0, there's no tendency to curl at all. Okay? And such a situation will be called irrotational. You can see the word irrotational. It does not have a tendency to rotate. Okay? There's no whirlpools, there's no eddies at P. So at point P, it doesn't tend to rotate at all. Okay. And it should have something here on divergence also. Yeah. Page 1107. Divergence can be understood in the context of fluid flow. If capital F of X, Y, Z is the velocity of a fluid, then divergence of F of X, Y, Z represents the net rate of change with respect to time of the mass of fluid or gas flowing from the point X, Y, Z per unit volume. So it's a tendency to diverge about a point, especially when you have a gas, a tendency to fill up the space, as we all know, right? So if you open up a bottle of ammonia, okay, as time goes by, the ammonia diffuses into the room, right? Okay, so there will be some divergence there. But if there's no movement, okay, divergence of F is 0, then there's no tendency for the gas or fluid to move. And it says capital F is said to be incompressible. If that's the case, there's no tendency for it to expand or contract. Okay. Well, contracting is, doesn't happen in general, right? It would be expanding. So fluids in general go from higher concentration to lower concentration, as we know, right? So if I open up a bottle of ammonia, then the smell will leak out to that higher concentration inside the bottle and then permeate throughout the room, and you start to smell it. And then as time goes by, the concentration gets weaker and weaker. So hence the divergence. But sooner or later, there'll be a time when the divergence is 0. So there will be no tendency to have any flow of the gas or the fluid. So I'm not testing you on that. And I'm not a physics teacher per se either. So want more details, ask your physics instructor. Okay. All right, so I'll show you number 7. F of X, Y, Z is e to the X sine Y, e to the Y sine Z, e to the Z sine X. Okay. So e to the X sine Y, e to the Y sine Z, e to the Z sine X. All right, so curl F is del cross F, sorry. The top is always ijk. I want you to write that. Second row is always partial with respect to x, y, and z. I want you to write that. And the only thing that changes from problem to problem is the p, q, and r. So e to the x sine y, e to the y sine z, e to the z sine x. All right, so I times that minus that, partial with respect to y. This doesn't have any y, so that's 0. Minus partial with respect to z. Partial, so derivative of sine is cosine, and it was a minus because I'm subtracting. So negative e to the y cosine z. Okay, then negative, because that's the way the j works. So there's automatic a negative. That times that, so to speak. But you're not really multiplying, you're just taking the derivative with respect to x. So e to the z cosine x. Minus that with that, derivative with respect to z, there is no z, so that's 0. Okay, and then that minus that. So partial with respect to x, there is no x, so 0. Minus the partial with respect to y. And that doesn't look right to me. Let's see, so what's wrong? Okay, that's okay, but that should be e to the x cosine y offhand, it looks like. I think I messed up again. The derivative with respect to y should be e to the x cosine y. So unless I'm doing something wrong, negative e to the x cosine y. And that should also be negative e to the x cosine y. Double check. That's 0. Derivative of this is e to the x cosine y. Yeah. Okay. So that's the curl. And you will notice this is not the 0 vector. So since it's not the 0 vector, we do not have a conservative vector field this time. Okay. Okay, then the divergence of f, del dot f. So by root, partial of p with respect to x, plus partial of q with respect to y, plus the partial of r with respect to z. All right, so partial with respect to x is the same thing, right? E to the x sine y. Partial with respect to y, same thing. E to the y sine z. Partial with respect to z, same thing. E to the z sine x. So there we go. Okay, notice divergence is a dot product. The thing that comes out is a scalar. But curl is a cross product. The thing you come back with is a vector. In particular, it's a 3-dimensional vector that we're supposed to have. Okay. All right, so that is that. These problems determine whether or not the vector field is conservative. If it is conservative, find a function little f such that capital F is del f. Find the anti-gradient. Okay. So we know what to do. Find the curl. If you do not get 0, don't bother to try to find an anti-gradient. It doesn't exist. Okay. Which is actually, looking at the time now, I'm going to show you 15. I was going to show you 13 and 15. 13 is more work. 15 is less work. So let me get the 15 out of the way, and then maybe we'll break and go from there. So 15. F of x, y, z is z cosine y plus xz sine y plus x cosine y k. I forgot to say I, j, and k, but I got too lazy. And of course, I'm going to write it the way I like it with the angle braces. Okay. I'm not sure why. There we go. I should. Yeah. All right. So, is this a conservative vector field? So we know how to do it in 2D. So what do we do in 3D? Find its curl. So curl F or del cross F. IJK. partial with respect to x, y, and z. PQR, z cosine y, xz sine y, x cosine y. Okay, so the I component is that minus that. So partial with respect to y is negative x sine y, minus partial with respect to z, x sine y. So I have negative x sine y minus x sine y, which is not 0. I don't have to go farther. Who cares what the others are? I do not have the 0 vector, correct? Even if this comes out to be 0 and this comes out to be 0, or they could both be 0 or non-0, it doesn't matter. I already have one component which is not 0. I do not have the 0 vector. That was pretty easy. Therefore, F is not conservative. Yeah, this dot, dot, dot again means therefore. Therefore, F is not conservative. I cannot find an anti-gradient, so I don't have to bother trying. Okay, so I'm just going to stop there and break. So after the break, I'll do one which is conservative. So you have to do this up and down stuff and find an anti-gradient. Okay, and we're actually I'm going to finish very quickly in 16.5. Okay, in which case I'll maybe 16.6 is a little bit longer. I'll sneak in 16.6 just to make things a little bit easier for you on Thursday. And besides, I have to make sure there's enough time for you to do the quiz. Okay, so the quiz will involve all this stuff up there. Okay, let me check to see if there's anything in the chat. Okay, so people that joined late, yeah, just go ahead and put your name in there. You're here, you're here. Okay, so we're good. All right, so we'll break as usual until 10 after. Okay. Okay, folks, let's pick up where we were. You check. So Kayla, I got you. Jerry, I got you. Vin. Oh, Vin, you were already here. Sorry, I see something else. Nicholas Chan, I got you. Elliot, Min, Rashan, and Kenneth, I got all of you. And anybody else join late? Let me know if I get you for attendance. Okay. All right, so let me get back to screen sharing. As I said, we're going to finish fairly quickly, I think. So I'll sneak in some of 16.6. It's a fairly deep topic, but what I'm going to share today, actually, some of it doesn't even have anything to do with the homework, but we'll see how it goes. Okay, so back to 16.5. I'll do number 13 for you because that is a conservative vector field. And how do I know? Because I did it. All right, so f of x, y, z, number 13 is equal to blah, 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 blah. And they put I, j, and k. I got lazy. And you know the way I like to angle braces. Okay, so if this is a conservative vector field, its curl is 0. So del cross f, or curl of f, partial with respect to x, y, and z, y squared z cubed. Well, this shouldn't be a plus even more since it's not I, j, and k, comma. 2x, y, z cubed, 3x, y squared, z squared. Okay, I, partial with respect to y, 6x, y, z squared, minus partial with respect to z, 6x, y, z squared, okay, 0. Then negative parentheses, partial with respect to x, 3y squared, z squared, minus partial with respect to z, 3y squared, z squared. That's 0. Then k, that minus that, partial with respect to x, 2yz cubed, minus partial with respect to y, 2yz cubed, which is the 0 vector, 0, 0, 0. Therefore, f is conservative. So that means I can find a scalar function, little f of x, y, z, whose gradient comes out to be this. So find that vector, anti-gradient, so-called. So that means this is fx, fy, and fz. So p, q, and r are fx, fy, fz. So fx is y squared z cubed. Integrate with respect to x. Well, there isn't any, so this is all constant. So x, y squared z cubed plus a function of y and z, g of y, z. So g of y, z, you can have all kinds of y's and z's as long as there are no x's. You know, y squared, z cubed, square root of y, sine of z, inverse tangent of y, z to the 5th power. Doesn't matter. The derivative with respect to x would be 0. Okay, now I differentiate with respect to y. So differentiate this is 2xy z cubed plus the partial of g with respect to y. And then compare with what I have, 2xy z cubed. Okay, so if this is going to equal this, that's already the same as that. That means g sub y is 0. Which means g of yz has no y to it. It still could have a z to it, though. Which now means f of xyz is xy squared z cubed. I now know there's no y, but there still might be a z, so we're going to call it h of z. Now I differentiate with respect to z. 3xy squared z squared plus h prime of z. Three xy squared z squared. So if that's going to equal that, that means h prime of z is 0. So yeah, the g of yz doesn't have any y, doesn't have any z, which means it's a constant in general. Okay, so we're done. F of xyz is 3xy squared z squared plus k. K is any constant. This k is just like the c. Remember in Calc 1 and 2, right? When you integrate it, it was blah, blah, blah plus c. Now it's plus k, that's all. You could say c, but the book uses k. I guess that's for multivariable. Okay, so double check. What's the derivative with respect to x? 3y squared z squared. Let's see, where'd it go? lost my place here. It's not right. There's no 3 there. That's right. There's no 3. I don't know how I stuck the 3 in there. XY squared Z cubed. I'm messing up left and right here. I'll get it right. At least I know how to double check myself. Okay, I think we got it now. XY squared Z cubed, which I had over here, but I wrote it wrong here. XY squared Z cubed. Y squared Z cubed. Okay, derivative with respect to X is Y squared Z cubed. Yep. Derivative with respect to Y, 2XY Z cubed. Yep. Derivative with respect to Z, 3XY squared Z. Okay, so now we're good. I think I had this right at first. 3XY squared Z squared. To partial with respect to Z, I'll get it right. 3XY squared plus 3XY squared Z cubed plus H prime Z, 3XY squared. Z squared. Three XY squared Z squared, 3XY squared. Okay, I think I got it now. All right, so it works. Okay, again for 15. Now, once I find one component that does not equal to 0, I can stop. Right? This is not 0, so I don't care whether the others are 0 or not. It's not the 0 vector, so we automatically do not have a conservative vector field. Okay, so quiz on Thursday will be stuff like this. Find the curl, find a divergence, show that you have a conservative vector field, a 3-dimensional flavor, and then if it is conservative, find an anti-gradient, and hopefully you don't mess up as much as I did. Okay. Okay, 19 and 21. Is there a vector field G on R3 such that curl of G is x sine y, cosine y, G minus xy? Explain. Okay, so P, Q, and R have continuous second order partial derivatives, very well defined. Okay. If there were such a G, then we have a theorem that says div of curl G is equal to 0. Here's curl G. So find the divergence of this. So the divergence by definition is a partial P with respect to X plus a partial Q with respect to Y plus a partial R with respect to Z. So derivative with respect to X sine Y. Derivative with respect to Y, negative sine Y. Derivative with respect to Z, 1. Sine Y minus sine Y plus 1 is 1. It's not equal to 0. Therefore, the answer is no. Okay. So again, the logic is there such a G? If there were, we have a theorem that says div of curl G is 0. But the curl of this thing came out to be 1, so therefore impossible. Okay, and last one, then I'm done. Then all I'll do is I'll introduce 16.6 and then we're finished. Show that any vector field of the form f of x, y, z is f of x I plus g of y, j plus h of z, k, where f, g, and h are differentiable functions is irrotational, okay, which means the curl of f is 0. There's no tendency to curl. It's actually very easy. So the vector function capital F is f of x, g of y, h of z, single variable. So the curl by definition is ijk, that's always there. Partial with respect to x, y, z, that's always there. In this case, p, q, and r are little f of x, g of y, and h of z. So the I component, that minus that. Okay. The derivative with respect to y, there is no y, so 0. Minus the derivative with respect to z, there is no z, 0. Same for all of them. Minus parentheses. Derivative with respect to x, there is no x, it's a function of z, so that's 0. Minus derivative with respect to z, there is no z, 0. And then k component is that minus that. Derivative with respect to x, there is no x, 0. Minus derivative with respect to y, there is no y, 0. So I get the 0 vector. So therefore f is irrotational. Okay. And we are finished with this section. Okay. So I'm going to mark off 16.5. Let me do my focusing thing. Will be done very soon. While I'm doing this, I believe I've gotten to the point where I can just average one section a day, which for the most of the semester I've been doing well beyond that from here on out. Although section 6 could get longer. Yes, there are some sections still to come that could get long. I try to avoid the quote unquote really long problems when I do this stuff. Okay. So I've done what I was hoping to do, which is 16.4 and 16.5. It's not even 7:30 yet. But if you just look at what I have in mind here, I can open up my little schedule. Okay, so if our last exam is here, I've got 16.6, 7, 8, and 9. I can do literally one section a day and we'll land just perfectly over here. But if something goes wrong, I take longer, I get sick or whatever, I still have one buffer day to push the test back to the 18th, although I prefer not to. Okay, so I'm going to put 16.6 here. But if I can literally average one section a day, then we're good. 16.6, 7, 8, 9 test. Okay. So let me introduce 16.6, and then I'll see if anybody has any questions. And if not, we're finished. Okay. Okay, what would the quiz be on? 16.4 and 16.5. So curl and divergence, conservative vector field in 3D, and find the anti-gradient of a three-dimensional vector. Okay, so sort of like problems like 1 through 7, and then problems like let's say 13. Yes, be fair. Okay, 16.6. Parametric surfaces and their areas. Okay, this can get really rich, but it's also hard to see what's going on sometimes. Okay, page 1111. So for a parametric surface, okay, we have parametric curves. For a surface, you have a function of two variables. R of uv is x of uv, y of uv, z of uv. You need to put that on your formula sheet. It's up to you. The main thing is you have two variables. Now we've had parametric curves where x, y, and z are a function of t. So you end up with a curve in space. Notice our position vector is x, y, and z. Okay, so again, the vector r is a position vector. The position is defined by variables. And when you had before x of t, y of t, z of t, that was like saying as time goes by, what's the x, y, and z coordinate? So as time goes by, I trace out a curve. But here you have what's sometimes called 2 degrees of freedom. You have two variables moving, u and v. That generates a surface. Okay. So 1 and 2, you want to put it in a cheat sheet, it's up to you. But for a surface, you have two variables. X equals x of uv, y equals y of uv, z equals z of uv. You have a parametric surface. Okay. So you might get something like this. So in the uv plane by the function r, you get a surface like this, let's say, R of UV. Okay, so that's not a curve. If you only have one variable like t, 1 degree of freedom, you trace out a curve. But if two variables can move, like u and v, you end up with a surface like so. And just show you what kind of neat stuff you can get. Okay, so that looks like a cylinder. It's a portion of a cylinder. Okay, there's a nice curvy thing right here. Right? Okay, and just showing you some pictures. So a surface like that. Don't worry, I'm not going to ask you to draw those. Some of you can do it. Some of you are good artists. I'm certainly not in that category. And of course, you can get spheres. Spheres, I guess they're trying to show you a little bit of the interior of a sphere. This is the unit sphere, x squared plus y squared plus z squared equals 1. And I guess they chopped off parts of it around z equals 0, so you can kind of, quote unquote, peek inside. But that looks nice, figure 9 there. Sort of like a world projection, right? A globe. And they even wrote it parametrically. X equals 2 cosine theta, y equals 2 sine theta, z equals z. So the two parameters are z and theta. And then it looks like this. So that means the radius is 2. More interesting shapes. Okay. Figure 11 kind of looks like a sinusoidal graph that's rotated about the x-axis. Remember doing volumes of a solid of revolution in Calc 2, right? Like take a sine curve, spin it about the x-axis, and you get a bunch of these guys. Okay. We'll be able to find tangent planes. Okay. So if you have a picture like this, we've seen this before, you can come up with a tangent plane, not a tangent line, but more appropriate to say a tangent plane. Right? Page 1116. Now, figure 13 is so weird. I don't even know how to describe it. But you can see at the particular point 113, they have a tangent plane. Okay, this thing is so weird, it looks like it intersects, doubles back on itself in some fashion, right? It kind of folds over. And you can't really show this very well with pieces of paper because pieces of papers aren't supposed to intersect each other and then keep going, right? So if you look over here, it kind of touches the rest of the graph, but it keeps going beyond that. Okay. But nevertheless, you can still talk about a tangent plane. Right, find a tangent plane. Okay, we can find r sub u and r sub v. Okay. If you want to put this on your formula sheet, you may, but it's really just the derivative of r. But we've seen that before. If you want the derivative of a three-dimensional vector, just take the derivative of each component, right? Partial of x with respect to u, partial of y with respect to u, partial of z with respect to u. Then r sub v, partial of x with respect to v, partial of y with respect to v, partial of z with respect to v. We've actually seen this before. You take the cross product, okay? Then you have to take the magnitude of the cross product. You might remember that we did that before. In the magnitude of the cross product, that was when we were finding the Jacobian. You might remember we did the Jacobian. That gave you the multiplication factor that you needed to have in order to change from one system to another. Okay. So formula for surface area on 1117. Okay, put this one on your cheat sheet. The one that says A of S is integral, double integral over the region D of, what does it mean when you have the bars? It's a cross product. Cross product gives you a vector, so it's magnitude. So it's the magnitude of RU cross RV. What is RU? Is defined there. Partial of x with respect to u, partial of y with respect to u, partial of z with respect to u. And R sub v, partial of x with respect to v, partial of y with respect to v, partial of z with respect to v. We've actually seen that before. It's really no mystery. Okay, you're going to add a vector with three functions. Okay, x, y, and z component. Fast, what's the derivative of the whole thing? Say guess. Well, how about I take the derivative of that one, derivative of that one, derivative of that one? You're right. Likewise, this. How do I take the derivative of the whole thing? There's three in one, right? We call it one function, but when you open it up, there's three parts to it. Okay, the x component, y component, z component. So how do you differentiate the whole thing? It's like part A, B, and C, or part X, Y, and Z. So there's three functions in one. We call it one function, and you open it up. There's three functions inside X, Y, and Z. Okay, so that's how you would find surface area there. Okay, then a special type of calculation for surface area. We've actually seen this before, page 1119. That's if you have Z as a function of X and Y, or the equivalent. You leave X alone, you leave Y alone, but Z is a function of X and Y, like Z is equal to, I don't know, X squared plus Y cubed or whatever. Okay, so they plugged everything in to compute it, RU cross RV, you get negative partial of F with respect to X, I minus partial of F with respect to Y, J plus K. Okay. And what's the magnitude of this? Well, the magnitude is the square root of that thing squared plus 1 squared, or 1 plus z sub x squared plus z sub y squared. And we've actually seen this before. Okay, but if you want to put this on your cheat sheet, you may. Okay, so this is the formula for surface area. We've seen that before, actually. Okay, so equation 9, A of S, the area of a surface defined where z is a function of x and y, is the square root of 1 plus z sub x squared plus z sub y squared. Okay, and you might recall, if you leave off just one of these, that was a formula for arc length. Okay, so if you add one more higher dimension, then you have surface area. Okay, so we've seen this before, but go ahead and put it back if you want. Surface area, integrate square root of 1 plus partial z with respect to x squared plus partial z with respect to y squared dA. Okay, and so you can find surface area of neat stuff like this. And you're integrating over the circle, it looks like, right? You have z as a function of x and y, plug it into that thing. Okay. Then the homework problems start. And unfortunately, the explanation that Mr. Stewart gives doesn't really show you how to do all these problems. So next time I'll show you how to do some of these problems. And I have to make sure I leave enough room for the quiz. Okay, so yes, I am to the point of, and I'm just about done. I'm blabbing just for a few more minutes. So we have just one section a day, I believe. But 16.6 kind of iffy. I'm not even sure if I'll be able to finish this. Now, if I didn't have to give you a quiz, I'd be able to finish this in time, but I want you to have plenty of time for the quiz, because it could get pretty long to do one of those problems involving curls and find as a conservative vector field and do the integration differentiation stuff. Okay, but if I don't finish on time, I can make it up later. By the way, I think section 16.9 is fairly quick. It looks quick and it actually is quick. So there's not really that much to that section. Okay, so otherwise I think I'm done. Okay, so Thursday, 16.6, and then a quiz. So in theory, 16.7, 8, and 9. If something goes haywire and I can't finish here, I can push it back to the 18th, although I'm leaning toward not doing that. Okay. All right, I'm officially done, folks. Let me check the chat. And got everybody's attendance? Anybody else came late? Okay, I think we're good. All right, any other questions? Otherwise, we're finished. Give you a moment to ask anything.
Yes, I had a question.
Mm-hmm.
Could you show me 19 and 21 for end of 16.5?
Huh?
16.5, 19, and 21, the ending part. Let's see. I'll just show you everything again. 19. And worst comes to worst is on the video. So there's that. Is that okay?
Yes, that's good. Thank you, Doc.
Okay.
Thank you,
Great.
Professor.
You're welcome. Okay. Anybody else, please? Either unmute yourself or put it in the chat. All right, I don't see or hear anything, so we'll call it a night. Okay, so we'll see everybody on Thursday. Okay, all right, good night, everybody. Bye. See
Thank you,
next time.
Professor.
Thank you very much. Have a good night.
Good night.
Bye.
Bye.